Hello, welcome to my channel. I am Ameya and we are discussing about control systems. Today we are going to discuss about mathematical modeling. And before going to mathematical modeling, let us discuss steps involved, the general steps involved in control system study. Whenever you try to study a system, you can easily divide it into three steps and then try to study that system. The first step is to analyze the system behavior. So that is the establishment of the requirements and the performance of the system which you want to analyze. Okay, then you go to the next step, that is called modeling of a control system, and we use modeling functions, differential equations, Laplace transform to model, mathematical model that system into the equations. And after developing those equations, we go to the controlling part, that is development of the control algorithm or suggesting a controller for that system. So any simple system, any complex systems, you can easily divide into these three steps and you can start analyzing those systems. Okay, so simple transfer function we have already seen in the various videos. Transfer function is basically the input output relationship of a system expressed in terms of s. Okay, so this g of s, which is in between r of s and h of s, the function which derives the input and output relationship, that is called a transfer function. Okay, now let us go to the mathematical modeling, and we are taking the first example, which is a tank discharge, a simple example. Now the system is very simple. There is a tank, there is an input q in, there is an output q out, and we are trying to develop some mathematical equation for this relationship between q in and q out. So this is what your establishment of requirements and performance. So we are doing here two assumptions. One is the cross section area is constant, which is A for this tank, and Q out is proportional with the height. Okay, so these are the basic assumptions which we are doing to simplify our mathematical model. And the equation which we are trying to fix is the discharge equation. Q in minus Q out will be the remaining volume, that is A into dH by dt. So volume will be again function of height, and then we try to convert everything into the function of height, so that q in minus kh, substituting the value of kh, is equal to A into dH by dt, and at the final you get q in terms of h, q in terms of h. So all the functions of h. So there is one function which is having a factor k, which is multiplied with the h, and there is one function which is time dependent, dH by dt, first differential with the area. So this is how we can convert a simple system into a mathematical form. Okay, let us take one more example, a simple example of spring mass damper system. Okay, there is a mass, there is a spring attached to it which is having a factor k, and there is a damper with a constant d. Damper will absorb the velocity, spring will absorb the displacement, and there is a force applied which is my input for my system, and you will get some displacement in my system. Okay, so we basically solve it like a mechanics. It's a simple system. We try to develop the equation, the free body diagram for the mass, which some forces will be going up, some forces will be going down, and the characteristic, sorry, the deriving equation will be Newton's second law. All the forces coming into system or going out from the system are equal. Okay, so let us understand the forces which are affecting. First is the inertia force because of the mass, which is Fa is equal to mass into acceleration. I can substitute acceleration at double derivative of displacement. Okay, then there is a damping force. Damping force will be Fd, and that Fd will give you d into velocity, that is dx by dt. And lastly there is a spring force Fs, which is a function of displacement. Applying Newton's second law, what you get is the mass ms square is equal to all the forces which are acting on the system. So mass into acceleration is equal to force. So mass into acceleration d2x by dt square is equal to the spring force which is in opposite direction, the damping force which is in opposite direction, and F in the downward direction. So here we are assuming the downward direction is positive and upward directions are negative. Simplifying the same, you can come up with a final equation, that is the second derivative of m into second derivative of displacement, d into first derivative of displacement, and k into x is equal to Fn. So basically what we are trying to do here is we are trying to convert every system into a differential form. Similarly, you can understand easily the electrical system, your LCR circuit, and you can derive these equations depending upon the capacitor, resistor, and indicator. And there are two variables that can be used. The rule will be voltage in will be sum of all the voltages passing through C, I, and R. And you can derive those equations in terms of two variables. One is called charge and one is the current. So this equation is for current and this equation is for charge. So this is how you can basically convert your system, existing system, into a mathematical model. We apply some standard rules on it, standard equations on it, and we try to get that model into one standard form. Okay, like a spring mass damper system, force is my input and displacement is my output. So you have to identify what are your inputs, what are your outputs, and then arrange those inputs and outputs so that you can have one transfer function with an equation. Okay, so this is what I want to discuss in this video. We will be looking of conversion of these differential equations into Laplace transform in the coming video. So if you like this content, do share my channel with your friends, subscribe my channel, check out the playlists which are available on my channel about the control systems, mechanical measurements, and industrial automation. Thank you for joining.